Okay, sweet. Hi, everyone. So this is the final review for data structures. So you made it this far. Pat on your back. Good job. And so the final exam will contain a lot of accumulative topics, which I'll give you hints on which one you have to worry about. But for now, we're going to cover like the main portion of the exam, which is all trees and graphs. So in this exam, you have multiple types of trees and multiple types of graph algorithms. So in this review, we're going to cover binary search trees, AVLs, graph algorithms including Kruskal's, Prim's, and Dijkstra's, and also at the very end, Huffman Code. Those are all the most important theoretical algorithms you have to worry about for the theory section. I'll make a separate video for the programming, so let's get straight into it. So for binary search is just holds a very simple property that every single node on the left subtree is less than the roots, and the right subtree is always be greater than the root. So it's pretty straightforward. I included a link to the visual itself. I'll add a code later, probably later tomorrow, maybe later tonight, on how to implement binary search trees as a class and how to do all the traversals as well in code. And because you have to worry about your programming section. So for time complexity wise, Um, binary search trees will always have the average case of log n whenever you're doing inserting, deleting, or searching. But for traversal, worst and average case will always be O of n. And for worst case, it will 100% always be O of n. So pretty nice to add this to your cheat sheet, but it's pretty straightforward stuff. And also with binary search trees, you have access to traversals. So there's four types of traversals you're gonna have to know well to perform them in the most adequate way possible. So we have pre-order. So first you will go towards the root first, and recursively go to the left, and then right subtree. So in visualizing, you go to the root first, then you go to the left hand side, and then you go to the right hand side. So nothing too complicated right there. If you do in order, you will do the left hand side first, then go back to the root, and then go to your right hand side, which is kind of nice. And then if you do post order, you always do left, then right, and then root. And then if you do level order, which is just BFS, so go from top to bottom. So you do the root, then you do left, then you do right. So, and a little note, whenever you do in order, you will always get the sorted order of that binary search tree, which is nice to know. So whenever you have an encounter an in order traversal, just know it has to be in order. So knowing that quick little theory, let's go to a mock question. So in the exam, you may be asked to insert values into a binary search tree and then give the actual in let's say a traversal. And for this case, it can be in order. So let's add 23 first. So given these numbers, let's copy this real quick and let's paste it down here. So when we add 23, it's pretty easy. You do 23, and then you're done. Yeah, so 23 is just the root itself. So we just add it to the top. And then we need to add 7. And remember, the rule is left-hand side is always less than the root, right-hand side is greater than the root. So 7 is less than 23. So that will go to the left-hand side. So we'll add it right here. We're good to go. 35 is bigger than 23, which is the root itself. So we need to go to the right-hand side. So we add 35 right here. When we add 12, we need to go we need to double check that the root is less than 12 because true, 12 is less than 23, but 12 is bigger than 7. Since it's bigger than 7, we need to put 12 on the right hand side of 7. And so from there, we need to check 3 this time. So 3 is less than 23, and 3 is less than 7. So we'll add 3 to the left hand side of 7. When we have 42, 42 is bigger than 23, and 42 is also bigger than 35. So we'll put it on the right-hand side of 35. Put 42 right here. And then when we do 18, we need to make sure 18 is less than 23. So 18, oops, less than 23. but it's bigger than 7. So 18 is bigger than 7 and bigger than 12. So it will go to the right-hand side of 12 itself. So we'll go right here. Sweet. It's your binary tree. Easy peasy, nothing too complicated. Just simple rules. For the left-hand side, it's smaller than the root. Right-hand side is bigger than the root itself. Pretty easy. And so, in this problem, we're told to get the in-order traversal. And so if we look back over here, in order involves us going to the left, root, then right. So that's your priority. Do left-hand side first, then the root, then you leave the right-hand side to the very end. So, paste in this little row right here. Let's go to the most left node, which should be 3. So we'll add 3 as our output. 3, comma, and remember, on the left-hand side of 3, there's no other nodes itself. So we'll go to the root. And the root of 3 is 7. So we'll output 7. And since 7 is the root itself, we'll go to the right-hand side. And for the right-hand side, we have 12 and 18. So we'll always go to the first appearance of that number. So it'll be 12, then 18. We'll recursively go back to 7. And since 7 has a root of 23, we'll add 23 as our root, and we'll print that out inside our array. And since the left-hand side is now complete, and 23 is the root, we need to go to the right-hand side. And so we'll add 35, then we'll add 42. So 35 is the first number we see on the right-hand side, and then we add 42. And that's it. That's your whole entire answer, which is kind of nice. So this is your binary search tree, and this is your actual traversal order, which is correct. Remember, in order will give us the sorted, um, the sorted binary search tree, which is true. We go from 3, 7, 12, 18, 23, 35, 42, which is true. This is sorted, so this should be correct theoretically. So maybe you may see a question like this on your exam. So just be prepared to know what a binary search tree is and know how to perform each traversal. And don't worry, I'll go through more traversals as we keep going. So for now, this is it for binary search trees. Let's move on to the next topic. So after that, we have AVL trees. So AVL trees is like a special version of a binary search tree, except it's self-balancing. So each node will have an additional balance factor, which is just the difference between heights of left and right. And the current bound, the binary balance factor could be -1, 0, and 1. And so there's a visualization here. I'll add the code later in the official PowerPoints. And the time complexity for AVO has an average case, exact same thing as binary search tree. However, when we look at the worst case improves a lot. So worst case and average case are both same thing. Will be log n for inserting, deleting, and searching. But traversal stays the same as O of n, as there's no way to actually improve that since we need to visit all the nodes themselves. So more on balance factors. Balance factor is not the same as height. Very important to know. And I will show you how they're very different. So we'll go into more detail later when we do the example. But just know balance factor is just the left subtree height minus the right subtree's height. Pretty easy, I swear. So there's a few rules. So whatever it's 0, it's perfectly balanced. You have the most optimized tree ever. Yay. If it's +1 or a positive number in general, it's very left heavy. If it's a negative number or -1 in this case, it's very right heavy. And whenever it's outside the bounds of -1 and +1, we need to do a lot of rotation. And so there are multiple types of rotations, and there's 4 of them. We have the left rotation, left, right, and right, left. Sometimes left, right can be known as a double right. Let me double check real quick. Yes, a left, right rotation can be known as a double right, and a right left rotation may be known as a double left. So just some terminology to know, as I may be referring them as double rotations and then left and right rotations. So keep that in mind. So I'll make a little note here. These are also known as double rights, and this is also known as double left. So I'll give like a formulaic version of these double rotations in case that makes it a little more useful, or you can just look back to the lectures and know how to do it like manually. So knowing that, let's go through a quick example. So we have an AVO tree and we want to insert all these values into that tree itself. So let's copy and paste this here and let's add the first value. The first value will always be 30. So I'm kidding. So whenever you get the first value, always add it as the roots. So 30 will be our root. Sweet. So from there, we need to add 20. Oh wait, also, my bad. So the current height of the root will always be 1. We will count that node as height 1. You can count it as height 0. Nothing wrong with that. As Zybook's covered as height 0, but for our case, we'll make it a little more simpler and start from 1 this time. And the balance factor for this tree will be 0 minus 0 because left and right subtrees do not exist, so they do not have a height. So your balance factor is height 0. So little keynote to memorize. Whenever you're adding a new node and that node has no children, you can always assume that the height is 1 and the balance factor is 0. So whenever we add 20, let's add 20 now, we can assume that it has a height of 1 and a balance factor of 0. Because as we said, 20 has no children on the right or left subtree. So height is 0 minus 0, which is 0. But however, we do need to update the height of 30 now. So the height will be 2, but the balance factor for this one will now be 1 minus 0 because the left hand side has a height of 1 and the right hand side is completely null. So it's 0. So now this is positive 1. As we said earlier, positive 1 means it's very left heavy, but it's within our range. So we don't need to do any rotations for right now. So currently it's still pretty balanced. Nice work. Now let's add 40 this time. So when we add 40, we have a height and balance factor for 40 is 1 again, and balance factor is equal to 0 again. So the height of 30 will stay the same. However, the balance factor now will be a little bit different now. So the height of the left-hand side will still be 1, but the right-hand side, we added a node. So that will be a height of 1 for the right-hand side. And so we need to do 1 minus 1, which is now 0. So our balance factor is 0 for all nodes currently. So it's perfectly balanced. Nice work. So now let's add 10. So following the same binary rules, we know that 10 is less than 30 and less than 20. So we need to go to the most left hand side for the node 20. So 10 less than 30 left hand side, less than 20 left hand side of 20. So go right here. Oops. So from here, we have a balance factor of 0 and a height of 1. The balance factor for 20 will now be a little bit more different. So the height is 2, and we have a left subtree, which has a height of 1. Right subtree does not exist, so it's 0. So we have positive 1, making it very left heavy. And for 30, the height is also different now. Height is now 3 with a balance factor of 2 minus 1, where 2 is the height of the left, 1 is the height of the right-hand side. So now will give us positive 1, which means it's very left heavy again. But it is within our range, so no need to do any rotations right now. It is still pretty balanced. It's doing a good job. So now we need to add 25. So 25 is less than 30, but bigger than 20. So we'll go to the right-hand side of 20, right here. So again, any new nodes we add will have a height and balance factor of 0 as it has no children, but The balance factor now for 20 now should be 0, since we know we have a child on the left and right hand side, which both have a height of 1. So it's 1 minus 1 instead of 2, 0. So for 30, 30 still has a height of 2. Nothing has changed there. And the right hand side still height of 1. So no change at all. The left subtree is perfectly balanced, while 30 is very left heavy still, but within our range. So we are a-okay. And now we need to add 22. So when we add 22, it's less than 30, bigger than 20, but less than 25 this time. So we'll add 22 right here with a height and balance factor of 1 and 0. But the height now for 25 will be 2, the height for 20 will be 3, and the height for 30 will be 4 now. So it'll be 4, 3, 2, and then 1 for 22. And so the balance factor now for 25 will be 1 minus 0. So the left-hand side does exist, but the right-hand side does not exist. So it's positive 1, very left-heavy, but still within our range. Here we have a balance factor of 1 minus 2, which gives us negative 1, which means it's very right-heavy, but still within our range. Sweet. However, when we check the balance factor for 30, we have height of left-hand side will be height of 3 minus 1, which is the right-hand side, give us positive 2, which means that is not within our range. We need to do a rotation. So given this tree, we know that it's very left heavy and it has multiple nodes. Since this involves this cannot be fixed within one rotation, we have to do a double rotation. And for this double rotation, it has to be a double right, or a left, then right rotation. So, so to show you this in a more algebraic method, let me try to make a little side note right here. So to do a double right, which is also known as a left-right rotation, we have this current formula right here, where we can say that, let's say we have x and y coordinates, where x will go over here. Well, my bad. Yeah, we have x, y, and z coordinates. Let's do that instead. So we have z as the root, we have y as the left subtree, and we have x as the right-hand side for y, where y has a child on the left-hand side known as y1, z has a child known as z1, actually named as z2, and x has two children, one on the left, one on the right-hand side, known as x1 and x2. When we do a double rotation, we basically want to make x as our new root, where y and z will be the children of x now. So y will be the left-hand side, z will go on the right-hand side. So in an algebraic method, x will be the new root, while z and y will be its new children. So y will go left, z will go to the right-hand side. So with the children now, we know y1 is less than y. So we can easily put y1 right here. And we know z2 is always bigger than z. So we can assume that the child of z2 will go stay with that parent right now. But with x1 and x2, let's do x1 first. So we know x1 is less than z, greater than y, but less than x. So we can also say x1 is less than x, but greater than y. So we can add x1 right here. We have x2. So x2 is less than z, bigger than y, and bigger than x. So we can assume that x2 will be on the right-hand side since it's bigger than x, but it is less than z. So we'll be going on the left-hand side for z. So we have x2. And that's it. This is how we do a double right rotation or a left-right rotation in an algebraic form. It's a little bit more different than the way the textbook talks about it, but it's another way of explaining how this tree works. So let me try to organize it real quick to show that this is a conversion. let's say like this, and then add a little red arrow like that. So when you make X a new root, Y and Z will be new children, and we will organize the children based on the actual placement they're at. So when in the case, it's double rotation. So let's add a formulaic equation for that as well. So we do double left. So we'll have the exact same x, y, z coordinates, where we'll have z at the root, y as the right hand side this time, and we have x as the left hand side for y. So z want to have a z1 on the left hand side, y will have y2, and x will have x1 and x2. So from here, it's very right heavy. So we need to do a double left rotation where x will be the new root again. So from here, we will put x as the new root. Then we'll have y as bigger than x. So y will go on the right hand side this time. Z will go on the left hand side since z is less than x. And since we know z1 is less than z, we could easily assume z1 will go on the left-hand side for z, and y2 will go on the right-hand side for y, as we know y2 is bigger than y itself. So now we need to worry about x1 and x2. So we know that x1 is less than x, less than y, but bigger than z. So we can assume that x1 is less than y, so we'll go to the left-hand side first, but bigger than z. So we'll put it on the right-hand side for z. That will be x1. So for x2, we know it's bigger than z, less than y, but bigger than x. So we can assume I'll go on the right-hand side since it's bigger than x, but less than y. So we'll go on the left side of y, will be known as x2. And so in a more algebraic method, this is how you would take care of a double left and double right rotation. So I know it's a little more differently than what the textbook covered, but in a sense, this should, if this makes sense to y'all, it should save you a little bit more time whenever you're like trying to wrestle these theory questions. So with that in mind, let's perform a double right rotation as this is very heavy on the left-hand side. So let's duplicate this real quick to remember what we were doing earlier. So to do a double right rotation, we need to move x as the root. So our current x in this formula will be 25. So let's remove all these balance factors for right now. And let's move 25 as the new root. And then 30 will be on the right-hand side since we know 25, well, 30 is bigger than 25. And then we'll move 20 on the left-hand side since we know 25 is less than 20, which is good to know. So move this nose over here, put this over here, boom. So we know, again, 30 is bigger than 25, but 20 is less than 25 itself. And so remember, 22 is going to be our x1 child, and x1 is to go on the left-hand side of y. So we can prove this as well by saying 22 is less than 25, so it needs to go on the left-hand side. And then when we go and then 20, comparing 20, we know 20 is bigger, 22 is bigger than 20, so it needs to go onto the right-hand side of 20, so lay right here. And so if we can see it visually, we know we have a pretty balanced tree. So remember, adding all back the balance factor and the height, where we know no children means has height of 1, balance factor of 0. So the height of 20 will now be 2 with the balance factor of 0. So we have height 1 on left, height 1 on right, making that 0. Height of 2 for 30 as well. But we have a balance factor of -1. Since left-hand side is empty, but right-hand side is not. So we have a height of 1. We'll make it -1, making it very right heavy, completely fine within our bounds. And 25 has a height of now 3 this time, with a balance factor of 2 minus 2. Since we have 2 on the left-hand side, height of 2 on the right-hand side, making that 0, making it perfectly balanced. So compared to our initial tree where we added 22, we can see that this tree is now rebalanced again. Sweet. We completed our objective now. Nice. So from here, we need to add one more value, which is 50. So when we add 50 to this current tree right here, we know 50 is bigger than 25, bigger than 30, and bigger than 40. So we know we need to add 50 to the right-hand side of 40. Add it right here. And since we know the balance factor of a new node is always height of 1, balance factor of 0, and we're going to have to update these heights now. We have a height of 2 this time, with a balance factor of 0 minus 1, making it very right heavy, so making negative 1, still completely fine. We do the balance factor for 30 this time. We have a height of 3, making balance factor of 0 minus 2, which is bad, making it negative 2. We're making it very right heavy. And so when we go back to 25 real quick, we know we have 2 minus 3, and that makes it negative 1. So making it very right heavy as well. So from here, and we know the height of 30 will also be 4 this time. So since we have an issue at this node itself, and we know the node itself is very right heavy right now, we have no inner nodes we need to worry about, which is like what this example had to do. And we only need to do one rotation, which is nice, which is only one left rotation, going from 30, 40, 50 to go in this direction. So to perform this rotation, let's copy this real quick, put it down here, delete the nonsense over here. And let's move around a few variables real quick while we try to rebalance this real quick. There we go. Nice. So we know when we do a single left rotation, we just have to move 30 as the left child of 40. 40 will be the new root, and 50 will still be on the right-hand side. So moving this around will be a lot easier than double rotation. So we'll make 40 the new root, moving it up here to the top, and move 30 down here, moving some variables around to make it a little bit more compact. There we go. We have this tree now. So the balance factor of 50 and 30 will be the exact same thing, which is good to know. Nice. So both of them have a height and balance factor of 1 and 0. 40 has a balance factor of now 0 this time, since both nodes exist with a height of 1, so that would just be 0. And the height for this value will now be 2. So we add a height. Now we check for height for 25. 25 has a height of 2 minus 2, making that perfectly balanced as well. And then the height will now be 3. That's it. Congratulations. You completed the first part of this question. Even though this one took a little bit more longer than binary search tree, that's okay. We just have to do, we saw how to do a double right rotation, and we also know how to do a single left rotation, which was what happened here. So I'll add a quick note here saying a left rotation. So if we want to do a more algebraic method, we can put over here saying a left rotation. We can say that we have z, y, actually, yeah, y, and then x. This will become, if we rotate to the left-hand side, will become y as the root, x, and then z. That's all we did basically. And for the right rotation, in case you ever encounter this in your exam, right rotation, it will be z as the root, then y, then x. It's making it very left heavy. So we need to do a rotation on the right hand side. So to do this real quick, It's pretty simple. We'll add an arrow signifying the results. We make y is the root, z will go on the right-hand side, and x will stay on the left-hand side. So it's not too complicated, I promise. It's just something you have to get used to, which is completely okay. So yeah, these are all the possible rotations you're gonna have to cover, and this is an example of how those are applied to this solution. So hopefully that makes sense. So let's move on real quick. So given this tree over here, we need to delete a few variables now. So let's copy this real quick, and we need to delete 25, 40, and then give the pre-order traversal. So let's paste this over here real quick, and let's delete 25. So a couple of rules when we're deleting. If a node, let me write this in a little note tab over here. So whenever we're deleting, if a node, so if a node has two children, a node has two children, always try to find the largest node on a left subtree to replace that node. So in other words, find largest node in the left subtree. So if you want to be more theoretical, you can also assume that we can find the smallest node in the right subtree. But in the lab you did for AVL trees, I mentioned that I coded that you can find the largest node on the left subtree only. So since the exam follows very heavily to the labs, I would recommend doing this step in here instead of doing the right smallest node on the right subtree. Both of these will give you the correct output, but since the exam is very time consuming, I would just recommend choosing one and stick with it. And for my case, I will stick to the lab version of this, and I'll just say I'm gonna find the largest node in the left subtree, and I'll replace our roots. So since we need to delete 25, we need to find the biggest subtree for that node. So on the left hand side, we have 10, 20, and 22. And compared to those three values, the biggest node we have is 22. So 22 will replace 25. So there you go. Yay. So, so we need to delete all this information over here now. And we need to update our balance factor now. So balance factor for 10 stays the same. Balance factor for 20 does not stay the same though. So that now has a balance factor of 1 minus 0, and that would be a positive 1 balance factor now, making it very left heavy, but it's completely okay within our range still. And for 22, balance factor of 2 minus 2, since we have height of 2 on the left, 2 on the right, making it 0, and the height will always be 3. So cool. It's completely balanced still. No need to do rotations at all. And so now, let's delete 40 this time. So to delete 40, same rules apply. So 40 currently has two children. Children children 30 and 50. And since 40 has two children, we need to find the largest node on the left subtree. And so when we delete 40 from this tree, we know the largest subtree on the left-hand side and the only subtree and only node on the left-hand side is 30. So we need to move 30 over here, making that the new node that will that has replaced 40. So I'll be like this. And so knowing that now, balance factor for 30 will now change. So the left hand side does not exist. The right hand side does exist. So it'll be 0 minus 1, making this very left heavy, right heavy again. But completely fine, still within our range. And 22 has the exact same balance factor and height. It's completely fine. So it has a balance factor of 0, so it's perfectly balanced. Nice. So we're almost done. Sweet, we started deleting a node now. So now let's actually do a traversal real quick. And we're gonna do pre-order this time. So quick refresher on pre-order again. Pre-order has a traversal of going to the left. No, my bad. Root, right, then my bad. Root, left, then right, in that exact order. So just take that priority. So basically, your priority will be the root, then the left, then the right. So knowing that, we know the root for this node over here that I will copy has a root of 22. So 22 will be our starting position, and we'll add that to our output. So output is 22. From here, we need to go to the left-hand side, which is 20. Since 20 has no right children, don't need to worry about it. And 20 and 10 are the only left on the left children on the left-hand side. So we can just assume 20 will be first, then 10. And since there are no right children for either 10 or 20, don't need to worry about that. We can move on. And then for 22, again, back to the root, we already know left is completed, so we need to go to the right-hand side this time. So the right-hand side has two values, 30 and 50, which are both perfectly on the right-hand side. So we're going to assume that 30 will be the next value, and then it'll be 50. And this is our pre-order traversal. And that's it. So nothing too complicated. Just remember who takes priority. So if we had, let's say, for example, we want to do a pre-order for this big root over here, we can easily apply the same rules. So let's copy this real quick. And you don't have to do this at all, but it's completely optional. So remember, pre-order for this bigger tree now this time. We know the root, then left, then right. Nothing else. So the root is currently 25. So we'll go 25 over here, add that to our output. And then we'll go to the left-hand side. And so the left-hand side again is always gonna be 20. And then when we go to 20, we'll go to the left-hand side again. So the left-hand side has more priority than the right-hand side. So we'll add 10. So 10, and from there we go back to 20, and 20 does have a right child. And so since the right has the least priority, we'll add 22 this time. And so back to the root, which is 25. We have completed the left-hand side, so now we can go to the right-hand side. So the first right-hand side value we see is 40, which is right here. And since left has more priority than the right-hand side, we'll go to 30 next, which is right here. We'll have 40, then 30, and then from there, we'll go back to the right-hand side, making it 50, which is now currently 50. And so this is your output for a more bigger tree. And so that's how pre-order works. And good job, you survived the first two topics. Yay. So now let's move on to a little more in-depth on graph algorithms themselves now. So, and within graph algorithms, we have a concept called spanning trees, which is a tree that spans an undirected and connected graph. Basically, a graph with no arrows. And so, spanning tree can be applied to weighted undirected graphs, basically edges with numbers within them. And with that, we can produce a minimum spanning tree. So, minimum spanning tree is a spanning tree with the least cost. Basically, it's a path that will be the cheapest and the least expensive, which is good. And two algorithms will create the minimum spanning tree, which is Kruskals and Prims. Kruskals, we'll go into more depth about those algorithms in detail, but just know minimum spanning tree, either use Kruskals or Prims. If we ever see the shortest path tree, which is a type of spanning tree, but however, we we want to make a path from the designated source node to any other node inside a tree that is the shortest path possible in an entire graph. Basically, we're gonna go from point A to point B in the most cheapest way possible. And so we have a few algorithms that we'll cover that will give us the shortest path tree. It includes Dijkstra's, Bellman-Ford, Floyd-Warshall, and topological sort. But however, for this exam, you don't have to worry about that. For topological sort, you need to know how it's made and what are the rules for topological sort. So, and since Bellman-Ford and Floyd-Warshall were only mentioned in this course, we will not be covering that as well. We'll only be covering Dijkstra's and topological sort. So let's move on to the first ones. So the first minimum spanning tree algorithm will be Kruskal's. And Kruskal is a very greedy algorithm where you're always gonna choose the smallest edge. And then one by one, you're gonna sort all the edges by its weights, add each edge one by one, smallest first without forming any cycles. If you do form a cycle, you need to backtrack and skip that edge for now. And so from there, we'll use a disjoint set structure to detect cycles. And then for the runtime of this, it's E log E, which is edge log edge, nothing else. It's only because the edge needs to be sorted. So that's why you have a time complexity that's very similar to sorting. So knowing that Kruskal's will always choose the smallest available edge, let's apply an example real quick. An example from the practice problems. So given this whole entire graph, let's draw the minimum spanning tree with the cost using Kruskal's algorithm. So let me just grab the solution I grabbed real quick, but just like this graph right here. Copy this real quick since I don't want to redraw this every single time. So this is our little gray. And so for the first tree, so so the rule of Kruskal's is always choosing the smallest. Let me write this down again. So with Kruskal's, you always want to choose the smallest edge possible every single time. So given this list of values, we have the values CD, which has a weight of 3, um, AF, which has a weight of 4, and we have DF, which has a weight of 5. We have AB, which has a weight of 7. We have BF, which has a weight of 10. We have CB, which has a weight of 11. AC has a weight of 16. And DE, which has a weight of 17. These are all our possible edges. And so we always want to choose the smallest one. And this is how you're going to sort it. And if you will ever code this has to be sorted. So we're going to trace the first one. So the first edge possible is CD3. So we go here to here. Oops, my mistake. Make this red. So we can say the first nodes we have visited is C and then D. So from here, we can mark that we have visited C and D. So we can say C, comma, D. From here, we choose the next smallest one, which is 4. And so 4 goes from A all the way to F. And so we can assume we have visited A, we have visited F this time. So A, comma, F. So next weight, next edge we can add is 5. So we go from D to F. So that's already been added into our vertex we have seen. So no need to modify this area over here, but we do need to, oh shit. We do need to add that edge, which is completely fine, which is good. So the next smallest edge from this list will be 7, which is A to B. So we go from A to B. So now B is our new node we have visited. So we'll add B. And so the next smallest edge now is B to F. However, remember, we cannot create any cycles at all. So, and sadly, this does create a cycle. The cycle is from A, B, F, and then back to A. That creates a cycle. So we cannot choose that edge and we need to cross it out. The next one. The next smallest edge is 11. With 11, we also create another cycle, which is a little more clearer to understand. So we just need to like reiterate how the cycle is going to be. At. So we need to mark that out as well. Cross it out as an edge we cannot touch. Then we have 16, where 16 is our next edge based on this greedy algorithm. And this greedy algorithm fails again, which creates another cycle. So we need to cross out 16 as a not possible edge. And then finally, we have 17, which is not the best edge, but it will finish our actual minimum spanning tree. And we can finally add E as the last vertex we have added to our solution. In the exam, you'll be asked to do this as well. However, since you cannot draw or put an image on canvas, you're gonna be asked to give me the order of the vertex you have seen based on this problem. So just try to follow this formula right here, where we first saw C and D first, and then we added um, A and F. So we added those right here. Then after a while, we got to B. So we add B, and then at the very end, we got to E. So this is how you're going to be inputting it to Canvas. Kind of important to know. So given our minimum tree, we have done it correctly. Sweet. So remember, cruise goals, always choose the smallest edge, sort them, and then start choosing from there. And remember, this is a greedy algorithm. It's not very optimized. So whenever you have a cycle, backtrack to the previous or just skip it from this list and go to the next one and next one until you have reached until you have made the minimum spanning tree. Nothing else. So this is how it's done in a more in a more longer way. You can do this in completely how you want to, but it's the minimum spanning tree. So another minimum spanning tree algorithm is prims. So with prims, this is the little bit more different this time. So we basically need to repeatedly pick the smallest edge connecting the MST to a new vertex. Nothing else. So here you'll be given where to start at. So let's say I want to start at A or 1. And then from there, given that access, we need to choose the cheapest edge that will basically unlock a new vertex. Nothing else. It's very similar to Dystra's. However, this uses a priority queue to pick this minimum edge instead. So here we have a V vertex plus E log vertex time complexity, only because we're using priority queue, so we need to use a binary heap. Nothing else. So using the same graph, let's apply Prim's algorithm instead. So given where we're starting at, let's start at A. So let's add this image over here real quick. Let's delete our previous solution. And a little note, whenever you do these algorithms, they should output the exact same minimum spanning tree. If they do not, that's bad. That means you did it incorrectly. So if you ever like get two different solutions, I would just recommend starting over from the very beginning. Because if you're not sure how to do it how to do it correctly, you may lose a lot of points. So I always recommend starting at the very beginning. So since it uses a binary um, priority queue, we can just assume that we need to choose the smallest edge this time. So let's let's output A, since A is our first starting index, and A has three possible edges. We have 4, 7, 16. And given this, the highest priority should be the cheapest vertex, cheapest edge, which is 4. So we'll add 4 as an edge we have taken. So we go from 4, so A to F, where F is now visited. So we can add F to the list of all nodes we have visited currently. And so F has two more nodes we can add. F has the nodes 5 and 10. So given these four edges, as we're going to keep accumulating these edges into a priority queue, which one's the smallest? And the smallest one between 7, 16, 5, and 10 is actually 5. So we'll add 5 into our actual path, and we'll add D, as D is the next vertex we have unlocked. We'll add D right here, highlighted orange. I'll put it as your solution on canvas. And then from here, D has access to two more nodes, two more vertices. So D has access to 3 and 17. So anything not highlighted in red between all of these now, we have 7, 16, 10, 3, and 17, which one's the smallest? And for this case, it's going to be 3. So we'll add 3 into our edge. And now we have unlocked C now. Nice. So we'll add C into our output. And then from here, C has unlocked only one new edge, as we already have the edge A to C already, which is 16. So no need to add duplicates. So we can just say C has unlocked 11. So again, between the edges 7, 16, 10, 17, and 11, which was the next smallest one. And in this case, the next smallest one is 7 now. So remember, this is given a priority queue. So we're always sorting about numbers onto the least expensive node. So we can always add this node now. Since 7 is our cheapest one, given that we're going to keep accumulating all the edges together. So now we add B, where B will go to the output. And now we have unlocked all edges now, which is completely fine, which is good. So again, given all these values now, we have 16, 10, 17, and 11. And if we follow the Prim's algorithm again, we need to choose the cheapest one first. So the cheapest one is 10. However, 10 creates a cycle again between A, B, C, and F, which is bad. So we need to ignore this and cross out 10. The next one is 11, but 11 also creates another cycle like last time. So we need to cross that out and say ignore that. 16 is the next cheapest one, which also creates another cycle, which is bad. So we need to ignore that and choose the next one, and the next and the final one is 17, which does not create a cycle, but and does visit all the nodes. So we'll add E again as our last node we have encountered. And if you compare solutions, this graph and this graph over here are the exact same thing. And your output may differ depending on how you do this, and also depending on how the graph is. But for our case, it's kind of the same thing, but it's, yeah, a little bit out of order, which is good, which just means you've done Prim's algorithm correctly, because those outputs should not be the same thing, but the graph output as seen here should be the same thing. So this should match this graph over here. But your output, which is this, should be different. So since they are the same thing, you've done both algorithms correctly. Nice job. So now let's move on to Dijkstra's. So Dijkstra's is another greedy algorithm that will find the shortest path from a source to every single node. This only works for positive edges, including 0 itself, but we don't count 0 because that's bad. And then from here, we will use a priority queue minimum heap instead to select the closest vertex. So in steps, we'll initialize everything to 0. Well, we'll initialize the source at 0, and all the other vertex will be infinity, because just to signify that we don't have access to that node yet at all. And when we do, we can modify it to an actual value itself. So we'll pick the vertex with the smallest distance and update the distance to all neighboring nodes. That's when we will update the infinity symbol. So since we're using a priority queue again, we'll do exact same complexity as prims. So we have v plus e log v. So given the same graph again, let's wrap this one up real quick now. So since we have to do multiple iterations of this graph, let's copy this and let's add a table this time. So to add a create a table real quick, we basically want to create a table that's all infinity except the source value. And so that source value should be 8, as the problem states. Or if you're not given a starting position, just always assume it's always going to be the most the first sorted variable in your problem. So if you have numbers, it should be 0 or 1. If it's letters, it should be 8 every single time. So given this problem, but here we're given a starting vertex as A. Sweet. So add A as orange signifies visited. So now let's add the infinities now. So we have A, B, C, D, E, F. And since A is our source, we can assume A is 0, and the rest are infinity. So from here on out, now that we know A is our source, we have 3 possible edges we can use. So we can use 4, even though it does look longer, it is the smallest value. Oh, my bad, 1 second. We have 7, and we have 16. So these are our 3 possible vertex edges that we have access to, and those 3 vertexes gives us access to C, B, and F. So let's go in order. So A will stay 0, B will not be different this time. So B, you can access through vertex, this edge over here. So from A to B, that's 7. So weight is 7 now. To reach C, we can go from A to C by going downwards, and that'll be the weight of 16 this time. And with 4, my bad. With D, it's infinity. We can't reach that yet. E, still infinity. But with F this time, we can go from A to F by following this arrow and that has a weight of 4. So, given that, this is our new table. Our table has been updated with all the possible numbers we can reach. And from here, remember, it's greedy algorithm. So we need to choose the smallest possible edge that will reach a new vertex. And for this case, between 7, 16, and 4, that'd be 4. So we'll add 4 as our vertex. So let's highlight this as orange. So this will be as chosen. So it'll be chosen now. So now this will be marked as red, as we've been using the color red the whole entire time. So let's use red for now. And so we can mark that as orange to signify has been visited. And also to give you the output, you can say A has been visited and F. So from here, we have access to a few more edges now. So we have access to F to B, which is 10. We have access to F to D, which is 5. So let's update our values now. So let's add our previous values. Actually, let's not add those previous values. Let's get them away from the table. There we go. So to reach B, we have 2 possible options. So we can reach B from A to B using 7, or you can go from A to F and from F to B, which has a weight of 14. And since this is the greedy algorithm, we always want to choose the smallest edge. And that smallest edge is 7, because 7 is less than 14. Because we always want to keep adding. So when we do this traversal, we do 4 plus 10, which is 14. But that is way too big. So we keep incrementing 7 into our list. So now let's see if we can get the other values now. So C has no other edge that we have access to. So that will stay at 16. D now is different. Now we have access to this time through 4. We go from A to F and from F to D. So that has a weight of 4 plus 5, which is 9. So we can update D with 9. Erase this now. And E, still not reachable at all because we have no access to those nodes. So we have to mark that as infinity. And F, we're already done with that. So compared to between 7, 16, 9, and infinity, which was the smallest? And that will be A to B, which is 7. So to reach B, we'll mark this edge as a node we have access to now. And we'll mark B as visited now. So we'll add that to our output. And now we can say B has been visited, so make this as orange. And so now after this, we have access to another edge now, 11. We have access to this edge now. Sweet. We have more options now. So let's update our values again. So C, we have 2 options this time. We can go from A to C using 16, or we can go through A through B and from B to C. But that has a weight of 7 plus 11, making it 18. Remember, Always choose the smallest path. And 18 is way too big compared to 16. So we'll just keep it as 16 for now. And we'll add that to update this variable to 16. And then for D, D has one possible option still, which is from A to F, F to D, which is still 9. So we can just increment 9 now since we don't have access to this edge at all yet. So we can mark that as 9. So to reach E this time, oops, we have one possible path. We have actually we have no possible path at all. So that's still infinity. My bad. So between 16 and 9, what's our smallest edge? And that edge is 9. So we'll add this edge now, 5, between D and F, make that as red, and add D as visited now. So we'll add D to our list. And since 9 is the possible value, which is from 4 plus 5 to reach D, we'll mark D highlighted orange to signify that we have done that already. Nice work. And now with D opened up now, we have 2 more edges we can add, the last 2, which is edge from C to D, which is now blue as possible, and D to E, which is 17. So we now given that value, let's see if we can update these values now. So C, same thing again, A through C, which is 16, B to C, which is 18, which we marked out. We just ruled out in the last iteration. But now we have A through F, oh, A through F, F through D, and D to C. So we have 4 plus 5 plus 3, which that should give us rough 12. Yeah, it should be 12, I think. Yeah, it is. So we'll say 12. So 12 is less than 16, which is true. So now we can update, hey, we have a more optimized path here. So we can say 12 is way better than 16. So we'll update C with 12 this time. D is done. Now we have access to E now, but we only have one possible solution still, which is A to F, F to D, D to E. So we have one possible solution, which is 4 plus 5 plus 17, which is 9 plus 17, which is 26. Now we have finally access to E, which is 26. And no, we cannot go through this path yet because we have not chosen 16 at all yet. So 16 is not a path we're taking at all. So we cannot go through this long way yet at all. So we can only do the longer paths when we know we're taking that path already. So basically, you don't want to take a detour at all. You want to stay on your route. Because if you take a detour, it's bad. You're basically not doing the most optimized path at all. So with that in mind, we have 12 and 26 now. 12 is smaller than 26, so we're going to choose 12 now. So the path 12 involves highlighting this path right here. So we'll change this to red. As beforehand, we had 4 plus 5 plus 3, which is 12. So we took that path earlier. And now values cannot be updated at all since we know, oh, we can update this where we have C. We're in counter C now, so we can add C to our list. But to go to E again, there is no other path. Since we cannot use these blues at all, we can only use reds. So we have 4 to 5 to 17 still, which is 26. And since 26 is our only option, we can finally say, in Dijkstra's greedy algorithm, we have created our shortest path tree. We'll mark that up. We'll mark this as now encountered E, and we have A, F, B, C, E, which is what you're going to input into Canvas. And like that, if you make a little note of it, it's the exact same graph as Prim's and Kruskals, but the order of the nodes is completely different. However, for this case, yeah, it's a little bit different. Wait, AF, BD, yeah, it's completely different. So the order, how you input into Canvas will be different, but the actual graph, this part will be the same. This is different. This is the same. So with that in mind, hopefully that made it a little more clear how dice rolls work. It's a very interesting topic, one of my favorites, but it can take a while to get used to. I won't lie, it took a while. But yeah, just create the table and just keep incrementing all the values to make sure you have like optimize your route. It's like 'cause you never want to take a detour. You never want to stay away from the path. You always want to make your path optimized. So that's all we're trying to do with dice stress. So now, given that, since I'm super exhausted, we have topological sort. Yay! So with topological sort, we have the following. I didn't even update that. We have the following rules. So topological sort only works for direct acyclic graphs or DAGs. Basically, you can't create a cycle. If you create a cycle, boo, you did it wrong. And every single directed edge from U to V basically must state U must come before V. So basically saying if we have, let's say, an example from 1 to 2, which is right here, 1 needs to come before 2. It can never become after. Nothing else. And little note here, there could be multiple valid topological orders, multiple of them. So in the review, I'm going to cover one of them, and the answer key for the slides and the graph practice problems, I gave a different DFS alternative, but honestly, all solutions are correct. As long as you don't create a cycle, we're good, and as long as it makes sense, we're good. So the topological process involves finding a node with no incoming edges, so n degree is 0. Choose any of these edges, so you can tie break whatever you want. I usually tie break as choosing the sorted option. So if you have A and B, choose A, and then from there, remove the node and its outgoing edges, or in other words, let's just perform DFS. Add that node to the stack, mark it as visited. From there, pop everything from the stack to an output stack or list. Complete doesn't matter what you want to do, but basically just an output variable, and then continue until the stack is empty. That's all you're doing. So from here, an important notes to know: if no nodes has 0 degrees, and my bad, if no nodes with n degrees of 0 exist, then the graph has a cycle, which means we cannot perform topological sort. So that's always the general rule. If there's no nodes of n degree 0, stop right there. You're basically done. So remember, nodes can be listed in multiple valid orders as long as the dependencies are respected, which is completely true. So, as I said earlier, answer key has one solution. This video has a different solution. So nothing wrong with that. So given this lovely huge graph, let's give the topological ordering for this directed graph. Remember, with directed graph, we have arrows. So let's apply this as this only works for directed and non-cycle graphs. So lovely. Let's give the name of this lovely graph. Let's find all n degrees of 0, which means no incoming edges. And for that, let's say node. Oops, there we go. Node. Oops. God damn. So with n degree of 0, basically no incoming edges. So let's look through each one of them. So we have A, which is a possible node. We have A, comma. Let's go in order. B also has no incoming edges. C does have incoming edges, so we cannot use that. D also has incoming edges. Oops. And we choose E. E also has incoming edges, so we cannot do that. F has like 3 of them, so we cannot do that one at all. G has 1, so not possible, and H doesn't have 1, so it's not possible. So given between A and B, you could be the tiebreaker, and I would always recommend going in sorted order. So the first value you should see is A, so choose A. So given that now that we have chosen A, let's duplicate this. Let's actually add this right here. So now we know nodes with n degrees of 0 or A and B, and we're going to choose A first. So now that we chose A, we can say that A, we need to perform DFS on A given in a stack. So let's create a simple stack real quick. Note that we have to perform DFS. So we're going to call this the call stack. And from here, we'll add A to the stack to perform DFS for A. And then, yeah. And from here, we're gonna go to the next value. To perform DFS, we need to go to the next value that we have not visited yet, which is F. So we'll add F to the stack. So basically, move the DFS aspect of this, my mistake, add A, and then call DFS for F. And from here, we have two possible solutions, C and H. I think I chose H as the alternative route, but let's go in order of alphabetical order. Let's choose C this time. So we'll choose C as our next possible node. We'll add C to the stack. So remove this DFS call, and we're going to put F to DFS for C. And so now C only has one possible vertex we have not visited yet, which is D. So add an arrow and D now. So we perform DFS one more time for D. But since D is the last edge, we can just say, hey, D, and we'll add C then D. D, we cannot perform DFS at all. Let's backtrack to the next possible node that has not been visited. So backtrack back to C, and C only has one output, which is D. So we need to backtrack a little bit more and reach F. Since F is part of the stack, we can still perform DFS as we have two optional routes, and that optional route was H. So let's add H this time. So again, performing DFS, let's add H right here. And so we have H to the stack, and we know if we backtrack again to F, F has no more children, and we reach A again. So DFS is completely done. We need to pop everything from this current stack into an output variable. So you just say output. Let's make this a list for now, and we can need to pop everything from here in that exact order. So it'll be H first, then D, then C, then F, and then A. That's your order. So A should be the top of this output, and H should be at the very end. Nothing else. That's why I added. That's why I may have said output stack in the actual answer key itself, but basically you just want to say A is at the top. That's all you need. That's all you need, which is good. So let me put top or front, whichever method of the queue you prefer, or stack, my bad. So given this graph now, we cannot do anything else now. Now we need to switch gears and choose the other possible node and degree set to 0, which is B this time. So now let's choose B as our node. We need to add to the stack. So let's clear up the stack real quick, but we'll keep the output as the same for now. So we're going to basically shift a little bit over here. So let's add B, perform DFS for B again. So DFS for B. And the next node we have not visited yet is both E and G. So we have a tiebreaker. So let's say we choose G. So if we choose G, that's bad. We have not visited all the nodes yet. And remember, the rules are U must come before V, which is bad because we have an incoming variable from E. So if we choose G, that'd be pretty bad. So let's just make a tiebreaker. What a tiebreaker is based on alphabetical order, which is E. So E, make a line saying this is the edge we took. And let's add E to the stack now. So erasing this real quick, adding B, then DFS on E, and then from E we can go to G this time. Sweet. We'll add G right here, and we go from E to G. Yay. So let's reorganize E again to the stack. E, and then G has no other possible outputs. We just name it G right here. And we're basically done with this one. Since we have visited all nodes, And since we have visited all nodes, we need to empty the stack and then put it to the output variable, which is output. So again, G will go first, then E, and then B. B should be at the front and top of this output variable every single time. So now that we have emptied our stack, we can say we can finally draw the topological sort as the order of our output should signify the order of which node should go first. So the first one in our output is B. So let's add B first. And B, after B, let's add E real quick. And then let's add G real quick. And we'll stop here for now. And we're going to basically modify our, actually, no, let's keep adding these edge vertices. So from G, we'll add A, then F, then C, then D, and then H. So from here, if we go in order, B has three, my bad, five outgoing outgoing arrows. So we have one from B to E, so we can just add a straight over here. B to F, so we can add an underline, going from B to F. B to G, so going from B to G. B to H, all the way over here. And finally, B to C. So we just add another arrow going to this variable right here. So that would be nice. Let's check E now. So E has two outgoing arrows, one to F and one to G. So we just go straight to G and add a loop going to F like that. Nice. And when we go to G, G has no outgoing, but we do have two incoming, and that does match with our current topological order. So since that's basically it for that n degree pattern, let's go to A now, the next n degree pattern. So A cannot have any no incoming variable arrows, which is true. Nice. So A only has one, which is to F. So we'll add a straight line to F, and then F has two. One is C, one is H. So we're gonna add a straight line to C, and we can add a really long line that'll go to H this time. And then D does not have my bad. C has one outgoing, which goes to D. D has none. H has none. Congratulations, this is your topological sort. Yay. So it's a very long process, but it can be done pretty fairly quickly. So yeah, this is topological ordering, which is my favorite um, graph algorithm we will ever encounter in this class. It's kind of interesting and makes it very useful for automated theory and embedded programming, where you have to use finite state machines. So with that in mind, whenever you are given a let's say a question about this, you may be asked like, "Hey, you may need to be drawn the top of the this algorithm right here, but we may be given a cycle." And so your job is basically to remember the topological rules, basic thing. You cannot have a cycle, and your job may be to remove a node, saying, "Hey, once you remove a node, will this create a topological cycle?" So just remember that, and remember topological sorting cannot have any cycles. You cannot visit any. You cannot have an arrow going backwards. So let's say like this. Bad. You cannot have that. Oh, my bad. You cannot have that at all. That's bad. You can only go to one from left to right, never right to left. So you can only always go this way from left to right every single time. If you go backwards, topological is wrong again. So that's why we have an output stack, an output variable to help you out, making sure this is the top and go to that exact order. So that's topological sorting. Let's wrap this up with Huffman code. So Huffman code is our last gritty algorithm we cover in this class, and is used for data decompression, which is kind of nice, kind of cool. It's very useful for embedded programming and operating systems. So you will see this again in OS, maybe as the first homework, hint, hint. And for embedded programming, you don't have to worry about this, but it's kind of nice if you want to add this into your projects. Makes it kind of cool. So the rule of thumb is to always have the smaller code for more freaking characters. So we have a character, let's say 4 times. The binary at most should be less than the least frequent one. So it should be hopefully but digit of 2. And then the least frequent ones should have a bigger digit, like let's say 5 to 4, like a lot bigger. So that's the general rule. That's just kind of a greedy algorithm since you want to choose the smallest one first, then leave the last one to the very end. From here, to build a tree, we always want to build a tree where each character has a leaf node. So basically the digits up here, I guess are leaf nodes, which will basically represent the current frequency for that the current frequency for that node of both the current frequency of both children, my bad, and the path from the root will always to the root that the path from the root to a character defines its binary code. So from here, left hand side will be zeros, right hand side will be ones, which we'll cover in an example. Don't worry, I'll go into more depth later. Here's a visualization. I'll add the code later. Don't worry about it. And for Huffman code steps, you want to create a node for each character. You want to insert to the priority queue by frequency. While there are more than one node, remove the two lowest nodes to the two lowest frequency nodes, merge them into one with their some frequencies, and insert it back to the queue. That's all we're doing, which I'll show you how to do it and tracing it. And keep repeating it until there's only one node, which is the root. Remember, and left branch is 0, right branch is 1. So general, really important notes to have. Characters with higher frequency will always be shorter. Really good to know. If you have bigger ones, you did it wrong. The resulting is encoding is a prefix free. So no code is a prefix of another. Never, ever, ever, ever. Remember, always group the smallest nodes together at every step when tracing, which I'll cover right now. So given this table, we need to create the Huffman code. So I'm gonna basically steal my old solution of the table I made earlier, this part right here, because this is the exact order of the table itself, except just more flat. So let's copy that real quick, add that to the review, and paste. So given this order, which is exactly as the table, let's perform Huffman. So remember, you always want to group the smallest nodes together. So the smallest nodes in this current table is A1, G1, M1, T1. So in that order, from reading left to right, let's group those two together. So we'll group A1 together, and G1 will be one node together. So to signify that, we'll take the sum of the frequency, which is 2, and that will be your leaf node right there. And that leaf node should represent the sum of the frequency, which is like that. And so we'll do the same thing for M and T. Add this down here. Oops, forgot about that. And then we'll add 2, duplicate. This is your leaf node for A1, G1, M1, T1. And so once you add these two together, you basically are removing this from the queue, and you're gonna add this back to the queue. But for visual sake, we don't need to worry about that. But we do need to worry about the next smallest node. So the next one, other than 2, is 2. So our next one in the queue is E2 and H2. And so for this specific order, we will put E on the right hand side and H on the left hand side. So we'll go here, and we'll put H on the right hand side. This is only because the Zybooks has a little more differently, and your answer should basically be the Zybook question. So to make it a little bit easier on myself, we'll just do it in this exact position. We have 4, which is 2 plus 2 from E, and then H is 2, and we have a leaf node of 2, which is 4. So this is our current Huffman tree. Basically, remove the smallest one from the queue, and add back your current tree together. So from here, we have the next smallest nodes we have is 3. Since 3 is smaller than 4, so we cannot combine these two yet, but we can combine the space, and we combine I, which is 3. So we'll create this, copy this, and this has a frequency sum of 6, which is 3 plus 3. 6. So once we added 6, we can add the next two nodes. But since you have three different trees now, we can do one step. We can do one step. We can kill two stones with one bird. Well, two birds with one stone, exactly like that. So let's do the first one. The first one will be 4 and 4. Since 4 and 4 are less than 5 and 6, we can add these two together to make 8. Right here and right there. So, and then on the right hand side, the other this tree over here, we can add 5 and 6 together. And since we know 5 is less than 6, we can put 5 on the left hand side and add these two sum together, which is 11. So add these two together, and this is the other tree. Nice, you're almost done. Just one more step, the last step, adding this all together into one root, which is 8. 8 plus 11, which is 19. 19 will add us into one big ass root. And remember, once you have one node, which is the root, you're done. You basically removed all the smallest nodes, which is the greedy part of the algorithm, and combine it into one root itself, which is this step right here. Which is true. Your root is 19, and from there the whole entire tree is built. Nice work. So now let's create the actual frequency for everything. I mean, my bad, the code for everything. So let's make a little subtable saying code. And so from here, remember our left hand side is 0 and the right hand side is 1. So let's go each step at a time. So let's do 8 and 11. The eighth leaf will have a binary digit of 0 and 11 will have a binary digit of 1. And again, let's do the left hand side first. So 0 on the left hand side again, which is leaf of 4, 0, and leaf of 4 on the right hand side is 1. So let's keep going to the leftmost root, and we have 2. The leaf of 2 is 0, and E is 1. So let's add E first. So E has a binary digit of basically 0, 0, 1. So E has a digit of 0, 0, 1. Good. You always want to make sure your bigger frequency has the least amount of digits, which is 3. Not that bad. Pretty good still. So let's wrap up the list, the most left edge. So A1 is 0, right hand side is 1. So let's add those two codes together. So A1 has a binary digit of 0, 0, 0, 0. So 4 digits. 0, 0, 0, 0, 0. Nice. So, and then let's check G now. So G has binary digit of 0, 0, 0, 1 this time. So G is 0, 0, 0, 1. And if you noticed, the 1, A and G both have frequency of 1, but they have the most digit, at most 4. Compared to E, which is only 2, has a frequency of 2, which has a smaller digit, which is 3, which is good. This is what your tree should be doing. Your tree should be giving more digits to the least frequency one, and the more frequency should have the least amount of digits. So we should follow that pattern. It's every single time. So let's wrap it up real quick. For the left-hand side, H2 is 0, so it'll be 0, 1, 0, 0, 1, 0. So H2 is 0, 1, 0. 3 digits again. Sweet. Keeping consistent with all the other frequencies. So, and then with 2, that's 1. And then M1 is 0 and T1 is 1. So M1 has a frequency of 0, 1, 1, 0. So M1 is 0, 1, 1, 0. Then T1 has a frequency of 0, 1, 1, 1. So T1 has 0, 1, 1, 1, which is good. Our least frequency should have the most digit compared to our more frequency, which have the less digits. which is currently 4 for ones. 2 has only 3 digits, which is good. And finally, let's go to the right-hand side where we have 0 for S5, 1 for 6. Let's finish up S5 now. S5 only has 2 digits this time. Nice. Just 1, 0, which is good. This is the most frequency one, so it should have the least amount of digits. Nice work. So let's wrap this up right now. And the space is 0 and I is 1. So we do this one more time. We do 1, 1, 0. So space is 1, 1, 0, 1, 1, 0. Nice work. And finally, let's clap this. Let's end it all by saying 1, 1, 1 for I3, which is only 3 digits. Good. 1, 1, 1. So this greedy algorithm always works by giving the most digits to the least frequency one and the least amount of digits to the more higher frequency, which is S5 only has 2 versus A1, which has 4, which is good. This tree is correct. Nicely done. So given this table now, we can actually encode this message now. So let me just delete this extra page here. Let me bring down the table we just made. So I'm going to cover the first couple of letters basically, and then from there I'll leave it up to you. So paste this. Oh, that works as well, I guess. Let me add this. There we go. Paste. It's a little bit janky, but it's okay. We can like modify it. Sweet. There we go. So given this message, this is the message. Let's encode this now. So we have the first value, which is T. So T has a frequency of 0, 1, 1. So our first digit should be 0, 1, 1, 1, which is T. So now we have H next. So H has a binary digit of 0, 1, 0. So it should be 0, 1, 0. Should be H now. So let me just fucking highlight this. This is H. This is T. And we keep using, let's keep flip-flopping between orange and blue. So I is next. So I has a digit of 1, 1, 1. So it'll be 1, 1, 1. Make this blue again. My mistake. This lowercase I. And then next letter is S. So S has a binary digit of 1, 0. So it'll be 1, 0. That'll be S. Now to add a space real quick, it's 1, 1, 0. 1, 1, 0. And that's the space right there. And let's add the lowercase I and then finish off the is part. So is, actually, we can keep going. So I again is 1, 1, 1, which will give us orange, which is the I part. Then we have S again. So S is 1, 0, just S. This is, we're almost done. We got a space again, which is 1, 1, 0, 1, 1, 0. Make this orange, that's your space. And let's put the his part. So his has an H, which is 1, 0, 1, which is blue. That'll be H. We have I again. I is 1, 1, 1. Then we have S again. S is 1, 0, 1, 0. And as you can tell, the more frequent you see it, the least amount of digits it should have. Like one more time, just to reinforce it. This is the last part. This is, let's shift down a little bit more. And let's get the final one, message. So let's add a space again. The space is 1, 1, 0. We're gonna duplicate this because it's perfect pattern. And let's do M. M has a digit of 1, 0, 1, 1, 0. 0, 1, 1, 0. That's M. Let's do E again. So E is 1, 0, 0, 1. So it'll be 0, 0, 1. That's E right there. And we have 2 more S's. So we can just say S. and then S again. We're gonna basically change the highlight color because we're extra like that. And we have mess, and then we have A, G, E left. So do A. We have 9 counted it yet, so it'll be 0, 0, 0, 0, 0. 1, 2, 3, 4. 4 zeros. And that'll be A. And excuse me for saying 0 multiple times. I'm very exhausted now. So now we need to add G again. So G is 0, 0, 0, 1. So it'll be 0, 0, 0, 1. I'm running out of space. This is the worst. Okay, shift one more time. Yeah, I'm going to shift. So shift one more time. There we go. And now let's do E, which is 0, 0, 1, which is 0, 0, 1. Nicely done. You did this correctly. So this is G and this is E. That's it. This is your very long binary digit. Oh, and that's it. You did it. This has been a very long exam review now, so let's wrap it up real quick. So some final notes, on the nose, is that remember the exam is very cumulative. So I would recommend all the technical things not covered in the review, including but not limited to hashing, sorting, and adding to an adjacent matrix and undirected graphs. Like all those like time complexities. I will highly recommend that. And like I said before, you may or may not be asked to do hashing again, but I'll give you a hint. It's not covered. It was not covered in the last exam, and I also didn't cover it in the last exam review. So given that little hint, you should be hopefully figure out which is the hashing you're gonna do. And yeah, so I'll let you know it was not covered in the last exam review or the last exam. So take that as you will. And for the programming section in the resource tab inside Discord, I may or may not have dropped a hint on the actual tree structure you're going to be doing, which traverse you're going to be doing, and which yeah, basically that's pretty much it I can say. So if you haven't looked yet, look in the resource tab, try the LeetCode questions, and one of those 4 LeetCode questions is the actual part of the function, and we'll give away the class of the actual question itself. Other than that, good luck. Try your best. You got this. It's a lot easier than the other 2 exams. I promise. It's just a bunch of tracing. It's very time consuming. But other than that, I'll do one more video on programming. I'll probably do it tomorrow whenever I have a chance. But if I don't get the chance, I'm so sorry. But it's been the last review for data structures. Good job, everyone. You're almost at the end. But that's it. Bye bye.